Let's now talk about optimization of contrast to noise ratio and signal to noise ratio. But first, the question is, how can we optimize the signal to noise ratio of our measurement? So one way that I want to talk about here is by repeated measurements. So let's say we repeat the measurements and we'll call them SI, where I is the index of the n repeated measurements. And now we obtain an average measurement. That's an average signal, which I call here S with a brackets. That's the sum of all the measurements divided by n. That's the standard definition of average. Now, the signal to noise ratio depends on, that we obtain here, depends on the square root of law. That law, I will briefly show where this comes from. So what this means is, if we do 4 repeated measurements of the same thing, we average them together, the precision of the measurement is improved by 2-fold. So let's just do a quick demonstration. For some of you, this might be standard theory from statistical courses that you may have taken. For others, it might be new. So we'll take here just a demonstration of this square root law. So I'll compose the ith measurement, one of the n measurements, as the true signal S plus a source of noise epsilon I. So for the third measurement, for example, S3, we have the true variable S plus a contribution of noise, which we call epsilon 3, now indicated by the index I. The expectation value, so on average, the average of the epsilon I squared is by definition sigma squared, and the other thing that we introduce is that the noise has an expectation value, the amplitude of 0, so epsilon I on average will average to 0, so it's not contributing to a systematic bias. So now S is the true signal, which for a moment is unknown. We have the average signal, which is sum of Si divided by n. This is equals to S, because it's n times S divided by n, plus sum of epsilon I divided by n. This is our average signal. Now we'll define here as the deviation of our measured signal, S here, minus the true signal, which we suppose exists. That is then equals to the sum of the epsilon I divided by the number of measurements. Now we will calculate the square of delta S squared. So that's the sum of epsilon I squared divided by n squared. And now we will dissect this sum here into different terms. We have the terms where epsilon I is multiplied by epsilon I, so this gives us a sum of epsilon I squared. And then we have a sum where I and j are not the same, so the error of the second measurement is multiplied by the error of the third measurement, etc. That's all overall samples. That's this term here. And now this term here is essentially the expectation value of epsilon I times epsilon j, and that goes to 0, because we have here that on average the error on average has an average value of 0. So if we multiply the error in the third measurement and sum it with the multiplication of the errors of all the other measurements, this is epsilon 3 times epsilon j, where I is not equal to j, then on average epsilon j goes to 0, so this term here goes to 0. And now we are coming to that delta S squared is equals to the sum of epsilon I squared, which is nothing but n times sigma squared, because we have had here, this term here. The sum of epsilon I squared is n sigma squared, and so we now have the error, the deviation, delta S squared is equals to sigma squared divided by n. Or in other words, the average amplitude of the noise, that is the deviation of our measurement, relative to the ground truth, the S, the average value, is given by sigma divided by root n, where n is the number of repeated measurements that we have done. So this gives us the square root law. So this means, this is known very well from statistics. I've re-derived here a fairly standard formula. What this means is that if we want to improve the signal-to-noise ratio by repeated measurements, we have to increase the measurement time. This increases the number of measurements, and to give you an idea, if you want to reduce the dimensions of your voxel by a factor of 2 in every one of the dimensions, so it's your voxel size that reduces the size by 8, and you want to increase to compensate for this reduction in signal with the smaller voxel that you have by an increase in the signal to noise ratio by a factor of 8, the square root of law tells you that you have to increase the measurement time by a factor of 64. So we go from a 2 millimeter resolution image to a 1 millimeter resolution image. 3-dimensional means we go from a 1 minute measurement, for example, to a 64-minute measurement, or 1 hour. Can you imagine that this is very uncomfortable? So now, second question was, how can we optimize the contrast to noise ratio? And here, for the purpose of this course, I will introduce a concept that is very important, and we will make repeated use of this approach that I will be demonstrating here. So, how do we optimize contrast? So we want to optimize the ability to distinguish between two tissue types. So we want to optimize here the experimental parameters of our imaging modality to maximize the difference between, say, signal S1 and S2. This is typically a complex and empirical procedure, not very easy. Sometimes we can actually deduce some useful information if the signal behavior can be modeled. Unfortunately, we have many situations where we can put a reasonable model of signal behavior to estimate the optimal contrast to noise ratio. And here what we will use is error propagation calculation. So we will look at a procedure now, and this is very important, this procedure. We will look at this procedure to optimize the contrast to noise ratio. The approach here consists of the following. Let's assume we have the signal or the measurement variable S, and we'll assume it's a function of two variables, k and t. Doesn't matter what they are. Well, we can imagine certain things. Let's say k is a tissue property. That's what we impose. K is a tissue property, that's important. And let's say it's a decay rate. Something is decaying. And let's say t is an experimental parameter. That is something that I, as an operator, I can change. I can manipulate that parameter. And here, for example, it could be time when we measure, for example. So we have decay rate and measurement time. Now the approach of finding the best contrast to noise ratio consists first in calculating by how much does the signal change if the tissue property changes. That is, we do nothing else than take the derivative of the signal with respect to the tissue property k. That gives us a measure by how much the signal changes if we change the tissue property k. We can of course not change the tissue property k, but in the end what we're asking is, we have a range of different tissue properties, and where is the imaging technique most sensitive to change differences in tissue property, here what we call k. So we'll take this function that we define here, we calculate ds over dk. That's the sensitivity of our measurement to changes in tissue properties. And then we want to find out where is it maximal. Because if we know that the signal change is maximal with respect to the tissue properties k, then we know we have the best possible contrast to noise ratio. And to find that maximum, we take standard calculus here, and we just find, for the maximum, we'll take the derivative of ds over dk, this function with respect to t, the experimental parameter. So first I'm asking, how does the signal change maximum with respect to tissue parameter, and then I have to find, with respect to the experimental parameter here, t, where is that change maximally. And that we do by taking the derivative. Then we just have to verify that we indeed have found a maximum. So let's take an example here. It's actually a fairly ubiquitous function, and we'll say our signal as a function of tissue parameter k and experimental parameter t is given by S0, a constant, times e to the minus kt. That's a very simple model. So where is this signal maximally dependent, the changes in k, where do they produce the biggest changes in signal? We can already look at this function and think about it. If we take, so But let's just go ahead here, and we'll take the derivative of the signal with respect to k. So we have the constant as 0, we have the internal derivative, t, and e to the minus kt. So we derive, remember we derive with respect to k. So now if we look at this function tells us at what point is this function most sensitive, to what extent is it sensitive to changes in the tissue parameter k. As if we look at this now in terms of the experimental parameter t, where I want to find the maximum t, where this is maximally, I can already deduce some behavior. If I let go t to infinity, so I measure at very long times, then e to the minus kt goes to 0, much faster than t goes to infinity. So t times e to the minus kt goes to 0 for t go to infinity. So we have, at that point, our signal is completely not sensitive to different k's. This is, in other words, saying here at kt versus infinity, this is a 0 no matter what the k is. On the other hand, if I choose t equals 0, this function here is 0. 0 times e to the minus 0 is 0. The function actually, it turns out, at t equals 0 is equals to s0. So it's s0 no matter what the k is. So I have no ability to distinguish the tissue parameter k at time 0. So neither at time 0 nor at time infinity do I have an ability to discriminate to tissues based on the parameter k. So now we want to find the maximum, so we'll take the derivative of this function here with respect to t and set it to 0. That's where we find the an extremum. We'll do the derivative, so that's standard derivation rules, product rule here, and then we can separate out s0 e to the minus kt, and we can see here we separate this out. We have this term here. This is never 0. We want to set this equals to 0, and to have this 0, we have to have the measurement at t0 equals 1 over k. So our ability to discriminate the tissue parameter k based on the choice of t is maximal if we choose t, the measurement variable here, so that is equal to 1 over the decay rate of our signal in this particular model. Well, this is fairly ubiquitous, like I said, and so the conclusion is for an exponentially decaying signal, the optimal time of measurement is equals to 1 over the decay rate. That is the best result in this case. Now, let's say we have two tissues with two different Ks. So we are getting two different optimal T0s, two different optimal measurements. So we no longer can have the best contrast to noise ratio for both tissues, and we have to find a compromise. How do we find that compromise? We can calculate it, but we can also ask ourselves, are we willing to sacrifice a certain percentage of the optimal contrast to noise ratio, that is the optimal sensitivity, and deviate a little bit? And so we're going to look at this now we're going to look at this function here, which is plotted here. So this is just normalized, so it has the maximum value 1, and on the x-axis we plot the variable kt. So we're plotting now this function normalized to 1 at the maximum. Kt equals 1 means that t is equals to 1 over k. This is the function that we obtain here. And luckily, if we are willing to sacrifice a certain percentage of contrast to noise ratio, let's say we are willing to sacrifice 20% here. 20% means we have, if we want to make up by repeated measurements, we have to go by the square root law. This means we have to scan 40% more. So we go from 1 minute to 1.5 minutes, 2 minutes, something like that. So this is not a huge penalty to pay. And now look at this function here. If we are saying we're going to stay within 80% of the maximum, then we go from essentially kt equals 0.5 almost up to kt equals 2. So roughly estimating here, we're gaining actually a 4-fold range in changes in the parameter k, that this parameter can change, and we're still very close to the optimal measurement conditions. We shouldn't be down here, and we shouldn't be up here, but if we are somewhere in this range, the penalty to be away from the optimal contrast to noise ratio is not enormous, and we can certainly live with that. So the choice of the exact measurement variable here, t, is not critical. It doesn't have to match exactly 1/k, and if we have two different tissues, it is not so critical if we are close to the optimum. This practically means if you have two different tissues with two different k's, then your t0 is somewhere between 1/k1 and 1/k2, somewhere between those two values. One can, of course, calculate that. So here's the optimum in the design.